Prostate cancer is the most commonly diagnosed cancers in the world and also holds the title of being one of the top causes of mortality in males within developed nations. The development of prostate cancer is the culmination of many different potential factors, including genetic, dietary, medication exposure, infectious disease, and sexual factors. The prostate's most important function is to secrete prostatic fluid, one of the components of semen, but this function becomes impaired during the development of cancer, in which the normal semen-secreting prostate gland cells mutate into cancer cells. It is classified as an adenocarcinoma. A wide range of evidence suggests that prostate cancer is initiated by prostatic intraepithelial neoplasia, which is characterized by cell proliferation within the gland ducts. As seen in the histology images, prostate cancer has a reduced number of basal cells compared to the normal one. This results in the basement membrane and the lumen structure to be damaged and distorted. Additionally, in prostate cancer, only a single layer of glands can be seen. This reduces the secretion of prostatic fluid.
The growth and proliferation of a cancer cell relies on the availability of iron within the cell. Our treatment takes advantage of this fact, and by regulating the amount of free iron available within the intracellular environment, we sought to interrupt the various pathways associated with such proliferation and growth. Previous studies have suggested for iron to be perceived as a potential chemotherapeutic target. However, the majority of iron-chelating agents target extracellular iron, which would lead to systematic iron deficiency and toxicity in our patients. Such studies have observed the effect of intracellular iron manipulation on prostate cancer cells in vitro, of which our treatment is adapted upon from, although there are currently no clinically available cancer treatments, despite there potentially being less adverse effects associated with such means. We attempt to introduce an iron chelator into the local environment to deny the cancer cell of iron reserves required for growth and proliferation. The chelator that we attempt to use for our treatment is that of dafapiran. Dafapiran is used as a means of clinically treating cases of thalassemia, kidney disease, and Friedreich's ataxia. It also shows much potential in its ability to treat prostate cancer, with previous studies successfully inhibiting tumor growth, progression, and metastasization in both murine and human castration-resistant prostate cancer cells. The aforementioned administration of DFP is usually taken orally, but is however associated with a slew of side effects, with the intensity varying from mild to severe, including vomiting, stomach pain, diarrhea, headaches, and a decrease in number of white blood cells, just to name a few. However, this is where the real novelty of our treatment comes into play, as instead of administering DFP orally, we attempt to administer DFP through the means of a nanoparticle directly into the cancer cell. By administering the chelator in such a fashion, we attempt to overcome the majority of the after effects associated with DFP through such means. DFP functions by interacting with the enzymes present in the Krebs cycle, causing the cycle to become disrupted, preventing the production of its normal functioning constituents. DFP removes freely available iron from the mitochondria of the cell and impairs the activity of an enzyme known as mitochondrial aconitase. This enzyme is responsible for catalyzing the isomerization of citrate to isocitrate within the Krebs cycle due to a class of high potential iron sulfur needing to be replaced periodically. It is through the depletion of high potential iron sulfur clusters by which DFP is capable of impairing the enzyme. The impairment of the essential enzyme in the Krebs cycle results in the impediment of the cycle and its potential products. Previous studies have shown that there is low aconitase activity associated with normal prostate peripheral tissue. This is proposed to be the result of its zinc-induced inhibition. The overactivation of aconitase is believed to be associated with downregulation of zinc transporters and is one of the early biochemical changes evident during prostate cancer development. This change leads to a shift from a previously citrate-producing to a citrate-oxidizing malignant phenotype, which is an early marker of mass cell proliferation and the eventual tumor progression. Such a phenotype has been previously observed to a great extent in various different human prostate cancer cell lines in previous studies. Recent evidence has already emerged hypothesizing that another TCA cycle enzyme, succinate dehydrogenase, may be susceptible to iron-mediated regulation, presenting another possible avenue in which iron is capable of inhibiting cell proliferation. It is also hypothesized DFP may target other intracellular iron-containing enzymes other than that of aconitase, such as the electron transport chain and ribonucleotide reductase, which may impact other cellular processes, leading to the inhibition of cell proliferation.
We will be inserting the iron chelator into the nanogel particle expressing chemokines which are specific to the tumor cell on the exterior of the particle. It will allow for the interaction between a nanodrop particle containing DFP and the tumour site. The nanodrop will be administered intravenously and will make its way to the tumour cell where it will release DFP. Hopefully, future studies should look at its specificity of receptors and antigens on both the nanoparticle and tumour cells, as well as address the ability of a nanoparticle to navigate the blood and be attracted to chemokines.